All right, let's dive right into this explainer and kick off our high-energy lab session on how the entire universe is constructed literally from scratch. Welcome to the lab, everyone. Today, we're tearing apart the fabric of reality to look at the ultimate microscopic blueprints of matter. And honestly, it's way wilder than you might think.
But before we fire up the Bunsen burners, I want you to take a quick second. Look around your room. Ask yourself how everything around you is physically held together by invisible forces. The screen you're looking at right now, the chair you're sitting in, the air filling your lungs, it is all built from the exact same fundamental Lego bricks, just combined in brilliantly complex, kind of chaotic ways. So let's figure out how those bricks actually snap together, shall we?
Section 1. Inside the atom. To understand this grand design, we are starting at the absolute bottom, with the tiniest building blocks of matter out there, the atom.
Here in the lab, our entire foundation relies on the atomic number. Now, this is strictly defined as the exact number of protons in an atom of an element. You can think of the proton count as the ultimate unforgeable ID badge. If you change the number of protons, you physically change the element into something completely different. It's literal microscopic alchemy. That atomic number dictates exactly who that atom is.
Okay, but what if you keep those protons exactly the same, so the identity doesn't change, but you pack in some extra neutrons? Well, that brilliantly illustrates our next concept, the isotope. By definition, isotopes are atoms of the same element having the same number of protons, but different numbers of neutrons. What does that mean for us? It means you can have different weights of the exact same element. It's like custom bowling balls. Some are heavier, some are lighter. But because their atomic number is identical, they all roll exactly the same way down the lane.
Section 2. Electron rules and orbitals. All right, now that we've got a solid, dense nucleus packed with protons and neutrons, we need to talk about where the electrons live, because they don't just float around randomly like some chaotic swarm of bees.
Electrons actually exist in specific three-dimensional regions of space called orbitals, and these correspond to very specific energy levels. We are primarily looking at spherical s orbitals, which are perfectly round clouds surrounding the nucleus, and then we have dumbbell-shaped p orbitals. Those align perfectly along the x, y, and z axes at exactly 90 degrees to each other. So it's less like a flat, predictable solar system and much more like a 3D cloud of mathematical probability.
So the crucial point here is that assigning electrons to these orbitals is exactly like filling a very strict, bizarre hotel. You must follow 3 unbreakable rules to build atomic configurations up to element 20. First, the off-bow principle. You always fill the lowest energy orbitals first. You got to start on the ground floor. Second, Pauli's exclusion principle. You get a maximum of 2 electrons per orbital, provided they spin in opposite directions. Think of it like 2 people sleeping head to toe in one bed. And third, Hund's rule. You must place 1 electron per p orbital before anyone starts pairing up. Everyone gets their own room before they're forced to share. Absolutely no exceptions.
Section 3. Decoding the periodic table. Let's zoom out a bit from the individual atom and take a look at the ultimate menu of the universe.
The periodic table isn't just some random list of ingredients. It actually displays elements in order of increasing atomic number, revealing repeating patterns, or periodicity, in their physical and chemical behaviors. It's literally a master code. An element's physical position in those rows and columns tells you exactly how its electronic structure is arranged. But to truly understand these repeating trends, we first have to measure our atoms. We define the atomic radius as the exact mean distance from the center of the nucleus to the border of the outer orbital. Simply put, it's the literal footprint of the atom in 3-dimensional space.
Here's the catch, though. Atoms don't always stay the same size, and they definitely don't always keep their electrons. If you want to pull one of those outer electrons away, you have to pay a toll. Ionization energy is the energy needed per mole to remove an electron from an atom in the gaseous phase. It is the exact currency you have to pay to rip an electron off. Some atoms give them up for super cheap, while others, they hold on for dear life.
Section 4. Periodic trends revealed. Armed with those definitions of size and energy, we can now uncover the secret patterns hidden right there in the vertical columns, or groups.
Let's look at the outer edges of the table and see how this builds across different families of elements. Look at group 1 and 2, our metals on the left. Their chemical reactivity actually increases from top to bottom. Why? Well, as the atomic radius gets bigger, those outer electrons get further away from the pull of the nucleus, making them way easier to lose. But flip over to group 17, the non-metal halogens on the right. Their reactivity decreases from top to bottom.
They desperately want to gain electrons, and it's much harder for the nucleus to grab a new one when the atomic radius is massive. It is just a beautiful, elegant, inverse relationship playing out right before our eyes.
Section 5. The rules of bonding. And now for the explosive finale of our lab session. How do these individual atoms actually stick together to form the solid, liquid, and gaseous stuff we interact with every single day?
It all boils down to chemical bonds. A chemical bond is a mutual attraction between two atoms resulting from the simultaneous attraction between their nuclei and their outer electrons, which results in a higher, lower energy stability. Basically, atoms are inherently lazy. They just want to be in the most relaxed state possible. To figure out how they combine to get there, we visualize their valence electrons using Lewis dot diagrams. By drawing those outer electrons as dots or crosses, we can see exactly which puzzle pieces are ready to interlock.
When nonmetals interact with other nonmetals, they form covalent bonds. This is the literal sharing of electrons between atoms to form molecules. They act like kids perfectly sharing their toys to build highly stable structures. This creates simple molecules like water, oxygen gas, or methane. They pool their resources so everyone gets a full outer shell. Win-win. But when perfectly equal sharing isn't an option, atoms will just outright steal electrons. This transforms neutral atoms into charged particles called ions. A cation is a positive ion made by the loss of electrons, while an anion is a negative ion made by the gain of electrons. By physically shifting electrons around, their electrical charges completely flip.
And this complete transfer of electrons creates our next category, ionic bonding. It forms cations and anions that have this intense electrostatic magnetic attraction between their opposite charges. This attraction locks them into an incredibly orderly 3D crystal lattice structure. The most classic example of this? Sodium chloride, which is literally just a table salt sitting right now in your kitchen cabinet.
Finally, metals have their very own special rule. They undergo metallic bonding, forming a rigid grid of positive ions that sit suspended in a free-flowing sea of shared, delocalized valence electrons. This brilliant structure is exactly why metals can conduct heat and electricity so well. It's why you can bend a piece of copper wire without it shattering into a million pieces. Those free-flowing electrons act like a flexible universal glue.
So, as we wrap up this explainer, I want you to look back at the room you're in right now. From the covalent bonds making up the plastic of your device, to the metallic bonds and the wires delivering your power, everything is just a chaotic collection of shared and stolen electrons desperate to find stability. Ask yourself, what chemical bonds are holding your personal world together, and more importantly, what's ready to react next? Keep questioning your universe, and I'll see you in the next explainer.